James Webb Space Telescope. The James Webb Space Telescope, JWST, is a space telescope designed primarily to conduct infrared astronomy. As the largest optical telescope in space, its greatly improved infrared resolution and sensitivity allow it to view objects too early, distant, or faint for the Hubble Space Telescope. This is expected to enable a broad range of investigations across the fields of astronomy and cosmology, such as observation of the first stars and the formation of the first galaxies, and detailed atmospheric characterization of potentially habitable exoplanets. The NASA Goddard Space Flight Center, GSFC, in Maryland managed telescope development. The Space Telescope Science Institute in Baltimore on the Homewood campus of Johns Hopkins University operates JWST, and the prime contractor was Northrop Grumman. The James Webb Space Telescope was launched on December 25, 2021 on an Ariane 5 rocket from Kourou, French Guiana, and arrived at the Sun-Earth L2 Lagrange point in January 2022. JWST is designed primarily for near-infrared astronomy, but can also see orange and red visible light, as well as the mid-infrared region, depending on the instrument. Objects near this Sun-Earth L2 point can orbit the Sun in synchrony with the Earth, allowing the telescope to remain at a roughly constant distance 19, with continuous orientation of its unique sunshield and equipment bus toward the Sun, Earth, and Moon. Combined with its wide shadow-avoiding orbit, the telescope can simultaneously block incoming heat and light from all three of these bodies and avoid even the smallest changes of temperature from Earth and Moon shadows that would affect the structure, yet still maintain uninterrupted solar power and Earth communications on its sun-facing side. The mirror is therefore composed of 18 hexagonal segments, a technique pioneered by Guido Horn d'Arturo, which unfolded after the telescope was launched. Image plane wavefront sensing through phase retrieval is used to position the mirror segments in the correct location using very precise micromotors. The actuators are critical in maintaining the alignment of the telescope's mirrors, and are designed and manufactured by Ball Aerospace and Technologies. JWST's optical design is a 3-mirror anastigmat, 36, which makes use of curved secondary and tertiary mirrors to deliver images that are free from optical aberrations over a wide field. In addition, there is a fine steering mirror which can adjust its position many times per second to provide image stabilization. The Integrated Science Instrument Module, ISIM, is a framework that provides electrical power, computing resources, cooling capability as well as structural stability to the Webb telescope. In some cases, it is possible to maintain a temperature low enough through the design of the spacecraft to enable near-infrared observations without a supply of coolant, such as the extended missions of Spitzer Space Telescope and Wide Field Infrared Survey Explorer, which operated at reduced capacity after coolant depletion. Another example is Hubble's Near-Infrared Camera and Multi-Object Spectrometer, NICMOS, instrument, which started out using a block of nitrogen ice that depleted after a couple of years, but was then replaced during the STS-109 servicing mission with a cryocooler that worked continuously. Correcting the flawed optics of the Hubble Space Telescope in its first years played a significant role in the birth of the JWST. In 1993, NASA readied STS-61, the space shuttle mission that would carry a replacement for HST's camera and a retrofit for its imaging spectrograph to compensate for the spherical aberration in its primary mirror. While the astronomical community eagerly awaited this mission, NASA cautioned that this extraordinary advance in working in space carried significant risk and that its successful completion was in no way guaranteed. In addition to recommendations to extend the HST mission to 2005 and to develop technologies for finding planets around other stars, NASA embraced the chief recommendation of HST and Beyond 77, for a large, cold space telescope, radiatively cooled far below 0 degrees Celsius, and began the planning process for the future JWST. Preparation for the survey included further development of the scientific program for what became known as the Next Generation Space Telescope, 78, and advancements in relevant technologies by NASA. This technology review represented the beginning step in the process that ultimately moved the project into its detailed design phase, Phase C. In April 2010, the telescope passed the technical portion of its Mission Critical Design Review, MCDR. The project schedule underwent review during the months following the MCDR, in a process called the Independent Comprehensive Review Panel, which led to a replan of the mission aiming for a 2015 launch, but as late as 2018. Assembly of the hexagonal segments of the primary mirror, which was done via robotic arm, began in November 2015 and was completed on February 3, 2016. In March 2018, NASA delayed JWST's launch an additional 2 years to May 2020 after the telescope's sunshield ripped during a practice deployment and the sunshield cables did not sufficiently tighten. The James Webb Space Telescope has 4 key goals. These goals can be accomplished more effectively by observation in near-infrared light rather than light in the visible part of the spectrum. For this reason, JWST's instruments will not measure visible or ultraviolet light like the Hubble telescope, but will have a much greater capacity to perform infrared astronomy. JWST orbits the Sun near the second Lagrange point, L2, of the Sun-Earth system, which is 1,500,000 kilometers, 930,000 miles, farther from the Sun than the Earth's orbit, and about 4 times farther than the Moon's orbit. But near the L2 point, the combined gravitational pull of the Earth and the Sun allow a spacecraft to orbit the Sun in the same time that it takes the Earth. JWST is the formal successor to the Hubble Space Telescope, HST, and since its primary emphasis is on infrared astronomy, it is also a successor to the Spitzer Space Telescope. On December 29, 2021, controllers successfully extended the deployable tower assembly, a pipe-like column, which moved apart the 2 main segments of the observatory, the telescope with its mirrors and scientific instruments, and the bus holding electronics and propulsion. Each panel consists of 3 primary mirror segments and had to be folded to allow the space telescope to be installed in the fairing of the Ariane rocket for the launch of the telescope. The primary mirror segments and secondary mirror were moved away from their protective launch positions. Segment alignment begins by defocusing the segment images by moving the secondary mirror slightly. Mathematical analysis, called phase retrieval, is applied to the defocused images to determine the precise positioning errors of the segments. To put all of the light in a single place, each segment image must be stacked on top of one another. Telescope alignment over instrument fields of view. After fine phasing, the telescope will be well aligned at one place in the NIRCAM field of view. 244. Initially, the individual primary mirror segments will be greatly misaligned, so the image will contain 18 separate, blurry, images of the star field, each containing an image of the target star. With the mirrors now positioned for almost correct images, they must be fine-tuned to their operational accuracy of 15 nanometers, less than 1 wavelength of the light that will be detected. 18 images of same target star HD 84406 by the 18 unfocused mirror segments. Phase 3 completion, showing 18 segments stacked as a single image of HD 84406. Images of sharply focused stars in the field of view of each instrument demonstrate that the telescope is fully aligned and in focus. Go programs are selected through peer review by a Time Allocation Committee, TAC, similar to the proposal review process used for the Hubble Space Telescope. A total of 460 hours of observing time was awarded to these 13 programs, which span science topics including the solar system, exoplanets, stars and star formation, nearby and distant galaxies, gravitational lenses, and quasars. A paper about the science performance from commissioning, released by NASA, ESA and CSA scientists, describes that almost across the board, the science performance of JWST is better than expected. The paper describes a series of observations during the commissioning, when the instruments captured spectra of transiting exoplanets with a precision better than 1,000 parts per million per data point and tracked moving objects with speeds up to 67 milliarc seconds per second, more than twice as fast as the requirement.